This is going to be tough. You're going to cry, and you're going to bleed. But it is up to you if it's going to mean anything. If you want to leave a legacy.
We knew this class wasn't going to be easy. We were cautioned and we were offered multiple chances to leave, but still, we wanted to be a part of it. The thing was, despite the countless hours of hard work, we knew it was going to be worth it. We believed it was going to encompass more than the design of the robot, and we were right. This class wasn't just about learning, it was about the development of a person.
It all begins with
we were tasked with the most difficult challenge yet. The CARPA initiative commissioned the completion of Project Thunderbird, a nearly impossible undertaking for high school students. We were essentially given less than 8 months to produce a fully functional dual-stage robot capable of entering a simulated volcanic environment to collect and transmit empirical data.
When we first started, we didn't know a lot. Although it's true that some of us worked with the robotics team, what we knew was also limited. Our sub-teams still needed to grow, and we still need more experience. Although we were focused on our own roles, we also branched out and helped with our team. Our little knowledge was actually to our advantage. We didn't know a lot, so what we knew, we used to create our own solutions. We weren't bound by conventional methods, so our solutions were quite unique.
Everyone had different ideas on how to approach the problem at hand, but we decided that we didn't want to regard any of them as impractical. So during our brainstorming sessions, we gave everyone the opportunity to voice their opinions. It wasn't until we did a QFD, or a quality function deployment, that's basically a design matrix that allows us to compare the advantages and disadvantages between possible solutions, that we were able to eliminate certain solutions. The QFD made it easier for us to isolate and identify the optimal solution for each problem that we encountered.
Our first ideas didn't really work out. This is exactly why the engineering process includes the testing and refining stages. It's rare for professionals to come up with the perfect solution right away, much less high school students, but we never gave up. To be honest, what we imagined the robot to be in the beginning of the year is not quite at all what it is right now. We had big plans for the robot, but the reality of things set in pretty fast. This didn't stop us though. We reevaluated our priorities and worked accordingly to our standards while never failing to keep an open mind. We don't want to meet just the standards. We want to exceed them. Setting the bar requires many hours of work, both inside and outside the classroom. Priorities such as machining and milling are dedicated to our allotted class time, whereas more organizational and managerial tasks are delegated to outside meetings. So aside from meeting class, we commit our free time to the completion of all tasks.
The only way we can truly achieve success is through teamwork. Each team member has a specific role, from managing finances to fabrication and machining. However, defining our roles doesn't restrict us from helping each other. We have roles to guide our focus so that there is workload balance between each subteam. The project scope is broad, so it's imperative that everybody plays a part.
One of the first things we did as a team was pick the names for our devices. Houston is the main device that has to enter the volcano and collect data. Eagle was our first generation data transmission device. Houston will first use its first entry system, the rotary excavation unit, to drill its way inside the volcano. Once it's inside the volcano, the environmental evaluation system will begin collecting data on the surrounding environment. In addition to this, it will trace the location of the target sample. It will then drive over to the target sample and use the specialized data retrieval unit to collect the required empirical data. In the event that Houston's main systems malfunction for any reason, the crisis aversion release protocol will initiate. CARPA will launch our escape vehicle, allowing it to enter range of our driver's station. This will allow us to retrieve the data that we collected inside of the volcano.
Designing the robot was a huge undertaking, but our team didn't leave us the critical task of designing all of it on our own. Different sub-teams gave us the feedback and ideas that we couldn't have thought of on our own. Having multiple perspectives on the project also allowed us to take a step back and really truly see the best for our robot. Although the robot's design was a culmination of the team's input, it was still our job as a design team to create the CADs and the CAMs to industry specifications. We had to develop a viable design while at the same time keeping in mind the aesthetics behind it, which led to constant redesigning of Houston.
Initially, we planned for Houston to have a carbon fiber shell, but we found that carbon fiber would not be a good option because it's too expensive and it basically shatters when impacted too hard. So that's why we have an aluminum shell now. Originally, we also designed a bicopter to fly out of the volcano, but we determined that to be too unstable, so we switched to the backup for fetching data, which is basically a baseball launcher in smaller size. Now, sometimes when you realize a design that you thought up in your head doesn't work, it's kind of depressing, or like everybody's like looking at you like, what is this? What kind of design is this? You're like, oh, well, I thought it would work. So you just go back to the drawing board and you think about it again, and you just get everybody's heads together and you come up with something better.
It was our job to make our ideas tangible. As a part of the manufacturing team, we made our conceptual design concrete and real. From the brainstorming concepts to the CADs and CAMs, we were the final stage that brought our robots to life. We pretty much machined endlessly, fabricating the robot piece by piece, and only created the parts of the highest quality. That was up to us. We felt that the highest quality materials were the best for our part. With every part we manufactured, we also assured that every angle was precise in every dimension and detail to create a robot that is simply perfect, I guess.
So as chief scientist, you're just basically supposed to lead discussion sessions and you're in charge of the overall design. But I found myself working with Dominic, our systems engineer, very closely, and machining and teaching people how to do some of the tricks I've learned around the machine shop during the time, and just leading everybody when we needed to be led in terms of machining and designing the robot. Yeah.
So as part of our outreach program, we decided to reach out to underclassmen at CAMS and provide them with an internship opportunity. We wanted to expose them to the ED curriculum before entering the class. We felt this would really help them open their minds and explore ways to use their creative juices in order to better prepare them to take on the class head-on. Their tasks were both big and small, but they always work closely with our team. For example, since our interns don't get the opportunity to present their part of the project during our critical design reviews, we assign them to research and present how to create the technical data packages to help refine their skills and our team skills as well. With the intern involvement, ED is something that's bigger than we ever thought.
Dot. Designed to inspire. And we needed to live up to our name. So the first of any EDD team, we started our own Dot outreach program. By reaching out to local youth groups and schools, we wanted to inspire younger students to become entrepreneurs and innovators as the future of the world. At outreach events, we start with an introduction on Project Thunderbird, showing the students our design and asking them how they would solve that problem. Then we continue on with the quality function deployment, a practical engineering tool. And in doing this with the students, we teach them that engineering is a process. And we explain to them that engineering design process. And we finish it off with a hands-on project, designing air-powered cars, and allowing students to think out of the box.
I had never worked on a team, and that was one of the skills that I was hoping to build. I could work with robots, but what I could not do was work with other people. And what EDD really did was help refine those skills and help me discover certain tools that I could use, not only in college but in life. And I really am glad that I can take away from that EDD experience and be able to utilize it and allocate those skills somewhere else in life.
When I came into ED, I already knew it was going to be tough. I knew it was going to be the hardest class I was ever going to take. I already knew I was going to cry about it. I already knew I was going to stay up all night about it. But what I didn't know was that I was really going to get something out of it, that it was really going to change my entire perspective on engineering and my perspective on working with a team and how hard it is.
Into the class at the beginning of your senior year, I had been a TA the year before, so I kind of knew what I was getting into, but you don't really know what's happening in the EDD class till you're part of the whole medley that is everybody running around, trying to get PO forms signed, trying to machine parts, trying to design the robot in time, and all that stuff. It gets really stressful and you don't see that until you're actually in the class.
I came into EDD with the expectation that there would be a large focus on building and designing the robot to complete the challenge, and there definitely was, but I think what was more emphasized than building the actual robot was understanding the process that we were going through. We could use this experience to help us learn the process that would allow us to engineer just about any challenge that we would face later on in life. In terms of just thinking about how engineering works, it changed my perception from thinking about it to where now I understand that it's simply a process that can be applied to any problem and solve just about anything that you can come up with.
This is, I guess, as real as it gets. This is how it's going to be in college, this is how it's going to be in the industry, and so yeah, I'm glad I was a part of it.
Guys that evolved our class, the outreach thing is going to be a permanent part of the class. Raise more money than any other class has. The kick pass, and I can't be more proud of you guys.
You want to do it?
Hey, I got it.
I guess I came in expecting to do something great, and I think we have done something great.